Hi, this is a solution for a situation in which a rocket is fired toward a wall at 77.3 meters per second at a 58.8 degree angle. The wall's 25.6 meters away and it stands 11 meters tall. And the question is, by how much does the rocket clear the wall when it reaches there? So to solve the problem, I'm going to share my screen and do this on a piece of paper. So first of all, let's take a look at the equations of motion. It's a projectile motion problem. So with the four kinematics equations, we're going to use this one for the x direction and these three for the y direction. And of course, the reason that I have these split up is because projectiles include motion in both the horizontal and the vertical direction, but those motions have nothing to do with each other. So we have to make sure that we keep the horizontal and the vertical motions completely independent. So I'm going to make a little drawing. The rocket starts out here and it's fired at 77.3 meters per second. And it's launched at a 58.8 degree angle. So some of that motion is in the x direction. We'll call that the horizontal velocity. And some of it's in the vertical direction. Call that VOY. Notice I haven't put an initial x velocity because whatever that x velocity is, it continues to stay at that velocity because there's no acceleration in the x direction. Vertically, there is acceleration due to gravity. So this velocity that we find here will only be at the instant that it's launched. So it's going to go up in the air and then come down somewhere. But there's a wall, and that wall stands 11 meters high. And it is 25.6 meters away. And the question is, how much does it clear the wall by? So this might look a little bit complicated, but what we're going to do is break it down into the two dimensions and see what we can do with it. So we're going to start by seeing what we've got in the x and the y direction. Now, if you're new to projectile motion, then one thing that you want to tuck away is that the acceleration in the y direction is always a given, right? Because projectiles are free-falling objects. That means that you always have the acceleration in the y direction is negative 9.8 meters per second squared. Now, what else do we have? Well, the problem stops here. So horizontally, we know that we're talking about a horizontal displacement of 25.6 meters. Okay, so we can put that over here. Delta x equals 25.6 meters. Now, in order to do a complicated projectile motion problem like this, you really need four givens. You have to have four givens. And I'll say this again, but at the outset, one of your strategies is usually trying to figure out how much time is involved. Like, how much time does it take to get here? And the reason I say you want to find the time is because if you can find the time in either dimension, you can use it in the other one. Because the amount of time the rocket takes to get from here horizontally, that amount of time is also the same amount of time it takes to get there vertically. So if you can find the time, you can use it on either side. Well, let's figure out these two velocities here. So the Vx is just going to be the overall 77.3 times the cosine of 58.8 degrees. Okay, so we've got 77.3 times 58.8 cosine equals, okay, so we got 40.04. 40.04 meters per second. Okay, so that's going to go over here. Vx equals 40.04. We can also get this initial velocity in the y direction. So VOY is that same overall 77.3, but this time times a sine of 58.8. Okay. So let's see, we've got 77.3 times 58.8 sine equals 66.12 equals 66.12 meters per second. And that is going to go over here. So VOY equals 66.12. And we have 4 givens now. So we're in business. And in order to find the time in the Y direction, you would need 3 variables because for each of these 2 equations that have time in it, there are 3 other variables. In the X direction, you only need 2 variables, and we have those 2. Okay, so let's figure out the time using the X direction. And from this equation, we get that time equals delta X over Vx. Okay, so let's recall, or no, take that back. Let's take that delta X, which is 25.6, and then divide that by the 40.04. And we get that it's going to take 0.639 time is 0.639 seconds. Okay, so 0.639 seconds. So that means from here, it's going to take 0.639 seconds to get to this spot. Okay, so what? Well, if we know the amount of time that it takes to get there horizontally, we also know the amount of time that it takes to get there vertically. So that becomes a given over here, 0.639 seconds. Now we can use these 3 variables to find the vertical displacement, right? If we want to find this vertical displacement, we've got the initial velocity in the Y direction, we have the time, we have the acceleration. So let's do that. And then we have to be careful because what that's going to give us is it's going to give us the vertical displacement from the beginning of the problem to here. So it's going to give us that distance there, that displacement there. But we're just looking for how much it's going to clear. So ultimately, we're going to have to subtract the 11 meters. Okay, so let's figure out the vertical displacement total. And that equals initial velocity in the Y direction times time plus 1/2 acceleration times time squared. So we've got 66.12 times our time, which is 0.639 seconds, plus 1/2 times negative 9.8 times 0.639 squared. Okay, so let's run those numbers and see what we get. There's our time, 0.639 times 66.12 plus half times negative 9.8 is negative 4.9. So 4.9 negative times that time squared equals, and I'm getting 40.27 equals 40.27 meters. Okay. So now that's the total displacement, but the amount that it clears by is going to be that total displacement minus that 11 meters. Okay, so the amount that it clears by equals 40.27 meters minus 11 meters, which is minus 11, 29.27 meters. We really only have 3 sig figs, so I'm going to call that 29.3 meters. And that's it. All right. I hope that was helpful.